Let's explore the sliding window technique. We'll start with a classic problem. Given the string abcabcbb as an array, what is the longest substring with no repeated characters? You might initially think of a naive approach checking every possible substring, but this leads to a time complexity of O and 2, which is far too slow for larger inputs. The sliding window technique offers an efficient solution. We use 2 pointers, left and right, to define a window within the array. We also need a way to track characters inside our window efficiently, like a hash set or map. The window starts at A, B, C with a size of 3. As we try to expand the window to include the next A, we find it's already present. This means our constraint is violated. We must shrink the window from the left, removing the first A. The window now shifts to B, C, A. We then try to expand again with B. B is already in the window, so we shrink again. This process, expanding the right pointer and shrinking the left pointer when a constraint is violated, continues. We keep track of the maximum window size encountered, which in this case is 34 ABC. Let's quickly trace another example. The string pw. Our window expands from P to P. When we encounter the second W, it's a repeat. So, we shrink from the left, removing the first W, making the window pwwkew. This is our longest substring with no repeated characters, giving us a length of 3. The key advantage of the sliding window technique is its efficiency. It reduces the time complexity to O, and as each element is visited by the right and left pointers at most a constant number of times. The space complexity is OK, where K is the size of character set, due to the hash set or map used to track elements within the window. The sliding window is a versatile pattern, useful for many problems beyond just finding the longest substring with no repeated characters. It applies to problems like finding the maximum sum subarray of a fixed size K, or identifying the minimum window substring containing all characters from another string. The core principle remains consistent: expand the window from the right and shrink it from the left whenever a constraint is violated. Continuing our look at create a visual explainer video on the sliding window technique. Let's revisit our initial problem. Given the string abcabcbb as an array, what is the longest substring with no repeated characters? The naive O and 2 approach is inefficient. Using the sliding window, we introduce a rectangle that highlights ABC. We label it window size equals 3. When trying to add the next A, we detect a repeat. So, we shrink from the left. The window becomes BCA. Again, we expand and shrink as B repeats, showing the dynamic nature of the window. For our second example, consider pw. The window expands to P. Upon reaching the second W, it repeats. We shrink the window, resulting in pwwkew, which is the longest substring with no repeated characters and has a length of 3. The key advantage of the sliding window technique is its efficiency, reducing time complexity to O, and because each element is visited at most a constant number of times. Space complexity is OK, where K is the size of character set, due to the hash set or map used for tracking. The sliding window is a versatile pattern, useful for many problems beyond just finding the longest substring with no repeated characters. It applies to problems like finding the maximum sum subarray of a fixed size K, or identifying the minimum window substring containing all characters from another string. The core principle remains consistent: expand the window from the right and shrink it from the left whenever a constraint is violated, including our exploration of the sliding window technique. The problem of finding the longest substring with no repeated characters in abcabcbb highlights the inefficiency of a naive O and 2 approach. The sliding window visually demonstrates its mechanism moving across the array, expanding and shrinking. We track characters in a hash set, map to efficiently check for repeats, ultimately finding the maximum window, ABC, with size 3. The pw example further illustrates the technique, showing how the window adjusts to find pwwkew as the longest unique substring of length 3. This technique offers significant advantages, achieving an O and time complexity by processing each element efficiently. It maintains an OK space complexity, where K is the character set size, due to the auxiliary data structure like a hash set. The sliding window pattern is broadly applicable, from finding the longest substring with no repeated characters to problems like the maximum sum subarray of size K, or the minimum window substring. All these problems leverage the core principle: expand the right pointer and shrink the left pointer when a constraint is violated, ensuring optimal solutions.